So up until now, we have learned that if a quadrilateral is a parallelogram, then this occurs. Well, now we are going to take that backwards. We're going to say, if the following properties of a quadrilateral are true, you can prove it's a parallelogram. So if the following properties of a quadrilateral are true, then it is a parallelogram. And we abbreviate parallelogram with a shape that looks just like a parallelogram. We will have some very similar properties. In fact, most of the properties from the page before are going to come right back into play for us. So let's start with this. Opposite sides of a quadrilateral are congruent. So if the opposite sides of a quadrilateral are congruent, then that quadrilateral is a parallelogram. But it's not just one set of opposite sides, it's both pairs of opposite sides. That's what you see up top. This is the side congruence that allows us to prove something as a parallelogram. In a proof, you would use it something such as, let's say this is A, B, C, and D. You would state the givens, all of the givens. So I'm gonna erase that and rewrite that in a different spot. So you know you've got your statements and your reasons. If I was to write a quick proof to prove something's a parallelogram using side congruence, I would state what we state is properties of a parallelogram. Do you understand? Does that make sense? So this is by definition properties of a parallelogram. So ABCD is a parallelogram by properties of a parallelogram, or by congruence properties for quadrilaterals, or by rules for parallelograms. Something of that effect. I would be pleased with your reason. We don't, because in many books it would be written down as like theorem 6.2. That's because it might be found in chapter 6, section 2, or theorem 6.7, and we don't learn it that way. So this is really just by properties of a parallelogram. And honestly, that's pretty much how most of these theorems are going to work. If the theorem is there, then the figure's a parallelogram by definition, by a property of parallelograms. So let's continue. Let's look at another one of these theorems. Our next theorem is going to read, if both pairs of opposite angles of a quadrilateral are congruent. So once again, we have some quadrilateral. So we will call this quadrilateral DUCK, all right? This is duck, quadrilateral. And if the opposite angles, if angle D is congruent to angle C, and angle U is congruent to angle K, then DUCK is a parallelogram, and it's a duck. See? We can turn a duck into a parallelogram. How would it be marked? Just like this. You would mark opposite angles as congruent. So, continuing. We have our third property, and it's bisecting diagonals. Once again, it's going to feel identical to what we've already done. If you have a quadrilateral, that's pretty ugly, and its diagonals bisect each other, then it is now a parallelogram by Properties of parallelograms, okay? So if you have a quadrilateral, first it must be a quadrilateral. If it is some four-sided figure, so if a quadrilateral has diagonals that bisect, it is a parallelogram. Final rule. If a quadrilateral has one pair of opposite sides that are both congruent and parallel, you could then prove that that is a parallelogram. But since we are not in the desire of proving every single little tiny step, we are going to be able to use this. If I were to ask you to prove this, you would need to use what we discussed earlier, which was drawing in a single diagonal, showing that that angle was congruent to that angle. That side is congruent to itself. The original opposite sides were already congruent, and then you could prove that this triangle is congruent to that triangle by side angle side. And that would prove this third side here, 1, 2, 3, 1, 2, 3, is congruent, and that would go back to our original rule, which is if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Okay?